So we're going to continue section 5.4 here, and we're going to talk about the mean value theorem for integrals. So I'm going to first develop it using really where we left off last time, the upper and lower bounds theorem, which basically said the area under the curve, so the definite integral in this picture that we see at the top, can be bound between an upper and lower bound that are essentially the inscribed and the circumscribed rectangles that we have here. So we had this rectangle that was in green, which was the inscribed, and then the yellow one's a little hard to see, but the yellow one was supposed to be the whole thing here, and that was the circumscribed rectangle. All right, so we could do the same thing down here. So essentially we can have this circumscribed rectangle, so the actual area under the curve could be bound above by this upper bound. And just like before, let's call this value right here, happens on this particular graph picture. The capital M, the upper bound, happens to come from the f of b, but in general, the area of this circumscribed rectangle is certainly going to just be its width, b minus a, times its height, which is just in general capital M. And so that is an upper bound on the actual area under the curve, so the definite integral from a to b of f of x dx. And then the lower bound is this inscribed rectangle. And so in this case, that inscribed rectangle happens to come from that lowercase m is where f of a is. But of course, the picture up above and what we did last time, it was a different picture, so it wouldn't have to. In this particular picture it does. So here's my inscribed rectangle, and so that is going to have an area of its width is b minus a times its height is lowercase m. So again, it's kind of when I shade over that, it looks like there. So that whole thing is the bigger one is the yellow one. All right, so now let's go ahead and just take this inequality, and let's divide all portions of this inequality through by that width b minus a. So we'll divide everything through by the width b minus a. All right, so when we do that, we're just going to have our lowercase m on the far left, and on the far right, we're going to have our upper bound there, capital M. And then those are our bounds. So really, I'm just restating those upper and lower bounds that we talked about last time. And that is a bound for, those are upper and lower bounds. But then I've divided everything through by b minus a. So we have lowercase m is less than or equal to 1 over b minus a times this definite integral from a to b of f of x dx. And that's less than or equal to capital M. So this quantity right here, so obviously that's what I'm talking about in both of those locations. So let's call that quantity asterisk. And so because that quantity is bound in between two real numbers. Now what I meant to do and neglected to do, and I do apologize here, was in general, on this picture it happens to be f of a and f of b. I meant to just delete that and call it lowercase m and capital M. So it won't always be a and b, so I wanted to change that. So in general, that is going to be bound below by lowercase m, and it's going to be bound above by capital M. Okay, so on our picture again here, so this is capital M, and this is my lowercase m. So that's my lower bound, and this is my upper bound. All right, so because this is just some real number, asterisk, is in between these other two real numbers, so these y values, if you will. So we have this continuous function on the interval from a to b, and we have these two different y values, so lowercase and uppercase m. Intermediate value theorem tells us if we are continuous on our closed interval here from a to b, that there has to exist some real number u. So there has to exist this real number u such that f of u is equal to this asterisk value, right? So this is my f of u right here, and so this is that asterisk value. So there has to exist some u such that f of u is equal to that particular value. So this particular value here, so that's, I don't want to use that same color again. So that is equal to, let me just write it out here. So this is equal to then f of u. All right, so what we have then is that f of u, there has to exist some u such that f of u is equal to this asterisk value, right? This real number value here between these two m's. So if I was to just multiply both sides of this equation by b minus a, I would have b minus a times f of u is equal to my definite integral from a to b of f of x dx. So this is the mean value for integrals. It says if a function is continuous on the closed interval, the mean value theorem guarantees the existence of u. There has to exist this real number u, and that's what you see up in the picture, such that this definite integral from a to b of f is equal to f of u times b minus a. Okay, so what's the geometric interpretation then of this? So let's just take a second and write that out. So this is really saying, so let's just write out here our geometric interpretation. So the geometric interpretation is saying our definite integral from a to b of f of x dx. All right, well, that is our area under the curve. It's kind of that area that's already shaded here, right? So definite integral from a to b, I'm just sort of reshading it in the same color. Okay, so this area right here, so that area that we see, so this is, in words, it's the area under f on our closed interval. So the area under the curve is equal to, all right, well now it's saying f of u, well f of u is the height of this rectangle here. So f of u is this height of this rectangle. So that's f of u, and then times b minus a. Well, that is the width of this rectangle. So the height times the width, that is this area of this resulting rectangle. So the area under the curve is equal to this area of the rectangle that results from that existence of u. So is equal to the area of this rectangle with height f of u. So that's the one I'm talking about. So that's our geometric interpretation, that there has to exist some value u in this interval from a to b such that the area of the rectangle is actually equal, the area of that resulting rectangle is equal to the actual area under the curve. So it's kind of a cool thing if you think about it, that there's actually just a plain old rectangle that would equal exactly the area that's under that curve. as long as that function's continuous. So no matter how, transcendental functions, e to the x or whatever kind of function you have on some interval from 1 to 3 or something, there will be a rectangle that will result, and that area of that rectangle will equal the area under that curve. So that's one way to think about, through those upper and lower bounds, getting to this mean value theorem for integrals. But you may have been thinking, we already had a mean value theorem, and we did, and it was more for derivatives. So this first little example is still really a continuation of almost the development of what we're talking about, just sort of a different way to come at it. So I want you to first recall what our mean value theorem was for derivatives, and then kind of connect that to the mean value theorem for integrals. So if you remember, your mean value theorem for derivatives basically said, well, first let's write out, it said if f was continuous on the closed interval from a to b, and if it was differentiable on the open interval from a to b. All right, and so if we had, I don't know, some sort of a function here, let's say, and suppose this is, a right here, and maybe over here is b, let's say. And so what the mean value theorem said is that there had to exist some value c. So the mean value theorem was about the existence of c such that the average value, or the slope of the secant line, would be equal to the slope of the tangent line at some point c in that interval. Okay, so let's say that's my c. So the c, the existence of c, was the conclusion of the mean value theorem. So mean value theorem for derivatives said, if these conditions were met, that there must exist this value of c that is in this interval from a to b, such that the f prime of, again, it's all about this existence of c, that f prime of c would equal the f of b minus f of a all over b minus a. Okay, there's mean value theorem for derivatives. Now, how could that get us to, you can see your mean value theorem for integrals written right up above there. So, how does that connect? Okay, well, I see that, what do I see in common, I guess I'd say. And one thing I see in common is the b minus a, but it's not in the denominator. So suppose I just made that very basic observation that, like, I see a b minus a in the mean value theorem for integrals, but it's not in a denominator. So I'm just going to multiply both sides and get it out of the denominator. So what do I really have here? I now have my f prime of c times the b minus a is equal to the f of b minus f of a. All right, so it kind of looks like, well, right now how I have it written, it's sort of looking like I'm maybe getting to something where I have the right-hand side, like I have a function, like the existence of some points, and then times the b minus a, but the other side, the definite integral, and then this f of b minus f of a. So what I want you to think about is our second part of the fundamental theorem of calculus. So I want you to recall that if you take a definite integral from a to b of the derivative f prime of x dx, well, first you take the antiderivative to evaluate a definite integral. So the antiderivative of f prime would be f, and then you evaluate between your limits of integration. And so here, that would look like f of b minus f of a. So this can then be replaced. So we now know we can replace f of b minus f of a with this definite integral of f prime. So this can now be replaced with the definite integral from a to b of f prime of x dx. So this now really looks essentially like our mean value theorem for integrals. The only thing that's really, the f prime is probably what's throwing us. So suppose I just say, okay, instead of calling it f prime, let's just replace f prime with g. Okay, so let's just say, let's let g of x equal f prime of x. And so now we would have g prime at c, not prime, that's the whole reason I replaced that. Sorry. Just instead of f prime, it's just g. So g of c times b minus a is equal to our definite integral from a to b of now just g of x dx. And so this now looks like our mean value theorem for integrals. So you can really just think about developing the mean value theorem for integrals, starting with the mean value theorem for derivatives. When you're done, kind of what, if I was to think about the graph, both of these are about the existence of this c. So like this starts off about there has to exist this c. There has to exist this c. And so now the main difference is I'm not really talking about the exact same function anymore, right? So g is the derivative of f. So back up here, I had, this was my graph of f, and now g is going to be the derivative of that. So I don't know, that kind of looks, f looks a little bit like x squared, looks like the right branch of a parabola. So just for practical and ease of, let's say that that's what it is. And maybe then this is my function here, we'll call this then g of x, because that would be like the derivative of that. And so then maybe this is, again, my, yeah, that's fine. My interval, let's say here from a to b. I don't know if that's been drawn exactly right here. But we're really looking at not a very good looking graph. Hold on just a second. This is taking more time than I wanted to. So here's, continue that up a little bit here. So again, this is my graph, for g of x. And so what the mean value theorem for integrals is now saying is that that same c is still, it's still the same c, right? But it's, now we're on kind of the derivative of f. So, but it is the same c number. That didn't change. So this c right here, the exact same c, this is going to be the same c whose then the area, that this is again our geometric interpretation here of the mean value theorem for integrals, says that the actual area under the curve from f of g of x dx from a to b is going to equal, so wherever this c is, its y value is going to be g of c. And so the area of this rectangle is going to equal, so this rectangle has the same area as the area under the curve. And this is obviously not a great sketch of this, and I apologize for that, but that's the idea of what we have here. So you can kind of develop the mean value theorem for integrals from the mean value theorem for derivatives. So just kind of a different way to get there. And then related very tightly to both of these is then what we call the average value of the function. So this value that we get, the existence of this C, or what we stated with the mean value theorem, the existence of U. So this value that back up in my original development here that I called asterisks here. So this value right here, which was equal to f of u, this is called the average value of f. So if once again, if we were just to kind of re-isolate, kind of going back and forth between these representations, if you were to rewrite this and again divide both sides by the b minus a, you know, what you're now getting is going to be isolating for that f of u, which sometimes is going to be denoted then with a y bar. So that is going to be the average value. So I don't know if you can make sure that y bar is significant here. So this is, again, this is the f of u value. Okay, so this f of u, this is equal to y bar. And so when we talk about it as being the average value, this is kind of another way that you could have maybe derived this. Certainly, we can take where we just ended, if you look at what's boxed up above, like in purple, and just divide both sides by b minus a, we're back to this other form. We kind of keep going back and forth here, but that's what we would end up with is now our definition of the average value here. Another way you can think about this average value is really what it means when we say average of a value. So you would think about the average of all of these y values. So if it was possible, so it's kind of another way to develop these same ideas. Like let's say I first just took maybe 1, 2, 3, 4, 5 of these y values, and I added up their y values and divided by 5. That might give me an estimate for the average value of this function over this interval. And then maybe I said, oh, well, 5 values doesn't really do very much. So maybe I add on, and maybe I take it up to 10 values or 15 values, and I add up those 15 y values and I divide by 15. And then I really let the number of values that I'm picking, so instead of doing 10 or 15, maybe I pick 100 values in this interval. So I'm taking 100 values here, adding them up and dividing by 100. So if I do that enough and I let n go to infinity, that's what we have down here. So it's letting n go to infinity of, and you see the f of, those are all of my y values. So this is inside the parentheses here. That's what I was talking about, averaging those y values. So what you see inside the parentheses is the averaging of a bunch of y values. Add up 100 of them, divide by 100. Well, no, that's not enough. Let's let n go to infinity. Now, what we're going to do is we're going to just multiply by a fancy 1. We're going to multiply by b minus a over itself. And then I'm also kind of breaking up the divided by n into little 1 over n's in each term. Then if we distribute through just the numerators b minus a. So suppose we take this b minus a, just that part of it, and suppose we distribute that through to every term inside those parentheses. That's what you see in the next row. Well, then what we know is that b minus a over n, all of those little guys, that's our representation for delta x. Well, this 1 over b minus a isn't going to be impacted as n goes to infinity, so we can bring that out as a constant multiple. And then we have this sum here, which I could even maybe factor out this delta x. But really, whenever, and I wanted to show it this way as well, because as you move into Calc 2, a lot of the applications that you're going to see developed are going to be limits of Riemann sums. And so when I have the limit of the Riemann sum, which is really what I have here, so if I rewrite this as, erase that. So if I rewrite this as my 1 over b minus a times the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I, and then times my delta x, that is our definition as the limit of the Riemann sum, here obviously assuming equal widths. And so that is our definition for the definite integral. So this is what you'll see a lot in calculus when you talk about like developing the kind of derivations of a lot of applications. It'll be anytime you see that limit of the Riemann sum, oh, that's my definite integral. So this was kind of another way to develop this notion of average value, which is the f of u. And so that f of u is then this, essentially the average of all the output values. So that's what we have right here. So this whole thing then, so our average value here, so this is what we're denoting as that y bar up above. And kind of think about this. Here's this infinite summing. That's what the definite integral, you can kind of think of it that way, from a to b of f of x dx. So it's this infinite summing of all of these like output values, and then divided by the width of that interval, b minus a. So it's adding up all these values and then dividing by the number of values, that type of idea taken to the infinite, right? And so that's where we end up with our average value. All right, so I know that was a lot of derivation because there's just several ways that we can come at this. So next time we're going to look at some different examples of finding the average value and or finding the value of u guaranteed by the mean value theorem. So that's where we'll pick up next time, is with some examples.